Good. Okay, I think it's probably time to move on to the next talk by George. Is that all right? If you have more questions, do put them in the chat and I'll answer them. Okay, thank you. So I'll hand over to George.
Okay, thanks very much, Siri. And thanks for organising this, and also to the Talmo organisers for keeping the show on the road. Hopefully you can now see my screen. So, as Siri was sort of trailing, I'm going to be going into a bit more detail on this tool JSXGraph, and in particular how I've been using that in stack questions in my teaching. So to start things off, not knowing what level of expertise people in the audience will have, and there is quite a spectrum, I'm going to start off gently and explain what stack is and what JSXGraph is. And then in the middle section, similar to what Siri was doing, I'll show you some examples of graphs that I've been using in my teaching. And then at the end, also maybe a bit similar to Siri, I'm going to do a bit of shameless self-promotion and talk about some research that I've been doing. So using some of these graphical interactive questions, I've been interested in what that does for students' learning. So I've been doing some research on that, and I'll give you a sort of flavour of some of the work that I've been doing there. Okay, so to start things off, what am I talking about? What is stack and what is JSXGraph? So stack is an e-assessment tool for mathematics. It provides a question type for the Moodle quiz, which lets you, as we saw in Siri's talk, have students type in algebraic expressions. And another really powerful feature of it is that you can randomize the questions that students see. So behind the scenes, you're using a computer algebra system called Maxima, which is a bit like Maple or Mathematica, but is open source. So you're able to use the power of that computer algebra system to generate random numbers and generate random mathematical objects and do things with them. And because you've got the students' algebraic input, then you can also use the computer algebra system to check the properties of that answer that they've given. So the grading that you can do in stack is really robust by checking the properties of what the students have typed in. So this example here that's on the right-hand side is just taken from the stack web page that I've linked to at the bottom there. So we can see the student's been asked to give an example of a function with certain properties, and when they get the feedback, stack is able to check the properties of that. And so it does, it has the correct y-intercept, so it's partially correct, but it's able to say the x-intercepts are not correct. So that's a feature that I've made quite a lot of use of being able to give students this tailored feedback on their answer. The second part of this is JSXGraph. So that is a JavaScript library. So it requires some JavaScript coding to create graphs using this tool. But lets you do things, I sort of think of it a bit like GeoGebra, which was the first one I was familiar with. Things like Desmos do this as well, where you can have interactive geometry constructions, and you can also plot functions as well, which is the main thing I've been using it for. So this is maybe scary to some people if you're not familiar with JavaScript. This is a big chunk of code to create that, that graph. Now, I don't know, I'm not really a professional coder, but I think quite a lot of it, certainly when I come to do coding, is copying and pasting examples that I found online, and modifying them, tweaking them to do what I want it to do. And the JSXGraph website has quite a lot of resources to get you started with that. So if you can find something on their documentation that looks a bit like the thing you want to do, it's quite straightforward to copy and adapt their code. So here, again, is another example. Don't worry if you don't really understand what's going on there, but the key thing here, which there were some questions about, is to what extent can you integrate these things? So we've got the stack is able to randomize things. So that's what I'm doing at the top there. I'm saying A is a random number with certain values, and then I construct a random function called fx, which is sin x plus this random number. So whenever a student load this question, they'll get a randomized value for what this function is going to be, and then the code below is going to plot it as a JSXGraph plot. So the students will see something like this, where they've got the question text, and within the question is this interactive graphic, which, as you can see, there's controls there that let them zoom in and pan around. But that depends on the values that were randomized in the stack question. So that's kind of one way of the interaction happening. When I change the random values in the stack question, they'll be reflected in the graph, and each student will see a different graph. So this was just an example of, it's actually in the documentation for stack. Here is a very basic example of how you can plot a function using JSXGraph. So that's just about the simplest chunk of code that you can have. Now, I was mentioning the grading feature. So this is a nice feature where, illustrating this, where the student types in the answer, the correct answer here, sign X, and they get the feedback, correct answer, well done. But if another student sees this as a cosine that's been translated, well, stack is intelligent enough to recognize that's also a correct answer. So that's in your power as a teacher to decide if you want that to be correct or not. But all I've done in coding this up is to say, is the student's answer algebraically equivalent to f of x? And in this case, Maxima recognizes those as algebraically equivalent, so the student gets the marks. If I wanted to be more strict and insist that it was based on a sine function, I could do that, and it's in my power as the teacher to decide how strict I want to be in the grading. Okay, so that was my whistle-stop tour of what is stack, the kind of main features of it, and how I'm using JSXGraph within stack. And I think the best way to see this coming live is to look at some examples. So these examples come from the course that I've been teaching. I think I've done it for 5 years now, Fundamentals of Algebra and Calculus. So this is a first-year course. The students take this as an option in their first semester, 20 credits out of the 120 that they do in the year. In the course, we cover topics from advanced high school mathematics, so A-level further mathematics or advanced higher mathematics in Scotland. Essentially, the course was aiming to get all students on the same page. So if they've either not done those courses at high school or had maybe taken their eye off the ball when they were in the final phases of high school and need a bit more brushing up on those topics, this is their chance to go into them in a bit more depth in their first semester at university. And the novel feature of it at the time was that it was being delivered entirely online. So this was before COVID-19. So we had this model already in place, and essentially delivering the course using a series of Moodle quizzes, which were providing the textbook content, but also mixing in interactive assessment questions where the students were getting feedback. So to deliver this course online, together with my colleague, Richard Gratwick, I wrote about 1,000 stack questions. So that covers all the kind of practice activities that the students do throughout the course, as well as all the assessment. And if you want to see more about the detail of what we did in that course, another bit of shameless self-promotion, here's my blog page where I've collected together various things I've talked and written about the course. And that link, I think, is on the next slide as well, so I'll move on. But these are all examples that come from the course. So because it's on this sort of high school mathematics, this kind of curve sketching and graphing and visualization is really important. It's an important part of that level of mathematics that we wanted to make sure was there in the course. So we've got some examples on the left showing cubics and quadratics and just plotting those. As I was saying, those are all based on randomization. So for the top left one, for example, the roots will not always be at -4 and -2. And based on what the roots actually are, the graph will update correspondingly. Same goes for all the other ones. So all these different graphs are randomized, so different students will see slightly different versions of the same question. Now, this poses a problem because you've got to come up with questions that are plausible. So this is a tip that I think will apply to not just using JSXGraph in Stack. I think this is maybe a tip that other people can use where they're randomizing questions in whatever e-assessment system using whatever graphing tool. If you've got one question that you like, then there's an easy way to make many randomized versions of it. So I've used this trick quite a lot where I find one question. This is a question that I know works and it has nice numbers. All the intersection points are integer coordinates. The curves and so on all have reasonable expressions behind them. So I can easily produce from this lots of different random versions of questions where I know the students will be able to work it through, and the level of difficulty and the types of expressions that they'll have to deal with will be consistent. So it's not that one student's going to suddenly have to have complex numbers or weird fractions to answer this question. So the way to do that is to start with this known question and then simply transform everything that appears in the picture to get your randomized version of it. So you can apply scalings, so dilating the axes, so shrinking or expanding, and also translations, so moving left and right and up and down. And based on how much randomization you want to do, that will reflect the sort of variation that you'll see in the output. So if I want to stick to having the coordinates A and B, for example, being integers, then I just make sure that my scalings and translations are all based on integers. And so that's what you do. You apply essentially this function to transform everything that appears in the picture. So I transform all the points by just applying this t function. So the point that was at 2 minus 4, which is, I think, the point the students are being asked to find in that question, the intersection of the line L and the quadratic, on the new version, the transformed version of that will appear at 1, 3 instead. And you can also do that to the expressions that appear. So rather than the minus x squared curve, the correct thing should be x squared plus 2x. And so Maxima will just work that out for you with this little magic bit of code, essentially just applying that transformation. So that's definitely a tip that I would recommend if you're looking to create lots of random versions of a question. Don't go pulling your hair out trying to construct lots of versions and checking if they look sensible. Start with one that you know works and move it around. There is one slight wrinkle to this with JSXGraph in particular, is about the bounding boxes. So the window that you're showing the students on this mathematical universe, you need to decide what the range of that is. So when you're creating a JSXGraph figure, one thing that I've highlighted there that you have to provide is this bounding box parameter, which specifies the top left and the bottom right corner of the picture, the coordinates of those. And if you don't set that into an appropriate range, the students will not see all the action happening in the graph that you want to show them. So it is important to get that right. And when you do this transformation, essentially you just look at where the top left and the bottom right corners go under that transformation, and that gives you for free what the new bounding box should be. So just for completeness sake, here's the code that I've been using to do that, with a little bit of tweaking. So you'll see there the BBX and BBY, I've added in minus 1.5 and 1.5, just to make sure that the origin always appears in the picture. So that's just been something that's just worked. It's kind of evolved over time that this has worked when I've been needing to make plots like this. So I figured I would pass it on. Okay, I'm going to move on now to look at slightly more interactive versions of it. So not just randomizing things so that I can show it to the student, but I want the student then to interact with the picture and do something with it. So I think for this, I'm going to move to different screen. So this is a demo site for Stack, which anyone can get access to. And I'll share this link at the end as well. So you can sign up for your own account on this site and self-enroll in this course. So you'll be able to see this. This was actually a talk I gave a couple of years ago at the EAMS conference, which was the more technical bits of what I've been talking about today. And I've added an updated version of that. As Siri was saying, things always move on. It used to be that to do this sort of interactivity that I'm about to talk about, you had to basically hack and write a lot of JavaScript code yourself. That's now been mainstreamed into Stack, and it's now a kind of core feature of the Stack JSXGraph integration. So it's much simpler actually to create these types of interactivities. So here was the example that I started off with, and the randomization that I was showing you just a minute ago. So they're all there for completeness as well. So moving on to the interactivity, Siri was already showing an example of this where you can have students interact with a slider and see the effect of that in the diagram. So I've had to code this up, obviously. What do I want to happen, as in changes? What will the effect be on the picture? I think actually this one was more or less a straight lift from something that was on the JSXGraph documentation, and I've just made some little tweaks here and there. But that sort of shows you how I was integrating these sort of things into the course materials as well. So this was the student's introduction to the definition of area under a curve and the Riemann integral, building in this interactive tool so that they could explore. So not just reading the text, but having something to do as well. This was an example slightly further on in the course where, as well as having something to interact with, I wanted them to have a question to answer as well. So based on having interacted a bit with this interactive applet, where they could see the Maclaurin series being plotted, so successive approximations of this function, they were then asked a question about which values does it seem to be converging. That's just a simple multiple choice question just to check, are they interpreting what I want them to be interpreting from that applet. Then we move on to slightly more advanced features. So these are definitely the parts that have been now integrated into Stack to make it easier to do this sort of thing, where actually what I want the student to do is interact with this diagram in order to give their answer. So I could ask them just to type in the coordinates of points A and B, which make an equation, which make a line with this given equation, but it's much more, I think, valuable for them to see that connection to visualization and have them actually plot the coordinates of the points and see the effect on the line. And I want to be able to do that sometimes to check the connection between the visual representation and the algebraic representation. So it's really useful to be able to now have that feature there. And there was a question in the chat a minute ago about accessibility, and that prompted me to look, and I'm just now using the keyboard. I can also move these points around. So I think there probably are issues with accessibility here. I've not done a full audit on this, but I think these things are only getting better. I'm not sure that was working in that sort of way a couple of years ago even. Okay, and I'm going to move on to a couple of other examples. So I want to show you this one here, where students are asked to plot the terms of an increasing sequence. So here's my increasing sequence like this. There we go. I can check it. Correct answer, well done. Now, actually, if I'd done something wrong, Stack could give me some feedback based on the answer that I'd actually given. So it, it knows basically this is sending back the values that I've put in using this interface, and then Stack behind the scenes is doing whatever I've asked it to do as the teacher. So as the teacher, I decided to give this feedback, and it may be that other types of feedback are better or more useful, and it's up to you as a teacher really to figure out what is going to be the best feedback that you can give students if they're making a mistake. So that was one example. I'll come back to that in a minute about the increasing sequences. And another example here is of having students plot the graph of a function. So by giving them these points and connecting them up with a line, the students are able to graph essentially a piecewise linear function from 0, 1 to 0, 1. And here I've got a sequence of tasks where they're asked to create examples of functions like that with particular properties, and I change the properties each time. So I'm going to go back to my slides to explain a little bit more about this example and the previous one with the increasing sequence, because that's getting into the topics that I've been doing some research on. Okay, so this was just in case the internet was down. We had, well, I guess I would have been stuffed on a Zoom call, but here we go. So these were the examples that you can see on the demo site. And I'm now going to go into looking at these two in a bit more detail. Okay, so this is all getting into, I think, where I see e-assessment having a real advantage over paper-based assessment is by getting students to generate examples of things. So, you know, this course that I've been talking about has 300 students on it, and if I get them all to give me an example of a cubic, that's going to be a bit of a nightmare for me to check. And I know that from bitter experience, where I got them to do that, and it was not so fun having to look through the examples that they gave. Whereas Stack can do that instantly and give students the feedback that I've designed for them. So this is based on some reading in mathematics education, some research that's, you know, this is a sort of hot topic to do with getting students to construct examples, being something that I think we've overlooked, perhaps. You know, we're missing a trick. So this book by Anne Watson and John Mason, I've been really inspired by, and they note that this is an important and effective pedagogical strategy, but whose potential is rarely exploited. So having students construct their own examples of mathematical objects is something that is being argued here can help them to learn, but we're not doing enough of. So this would be more nerve-wracking if we were all together in a room where it's a sort of audience participation moment. This was an example actually that John Mason, I've seen him give in a talk. So if you've got a bit of paper in front of you, why not sketch a cubic and see what you come up with. And now sketch one which doesn't go through the origin, so probably the one that you instinctively went for goes through the origin. And now do one that's monotonic. So you probably went for one that was not monotonic. And now what about one where the inflection slope is negative? So I don't know how your experience of that played out, but certainly when I first did this, it felt like John was able to read my mind and sort of know which were the obvious examples that I was going to go for, and rule those out with the next prompt. And that is a sort of general pattern that is recommended in the book, of using this technique of asking students to give an example and then adding some constraints, guided by your understanding perhaps of what are the more obvious examples that they might give, and trying to rule those out. So you keep adding constraints or asking students to come up with another example or one that's different in some way, with the aim of trying to enrich the students' space of examples that they're familiar with. So moving beyond the obvious familiar ones, maybe pushing them into recognizing new things as examples that they may not have considered. So into the shameless self-promotion. So this is a couple of pieces of work that I've been doing related to this. So the first example that I was showing with the increasing and decreasing sequences was part of this study where I actually, in this course that I was just talking about, was wondering, is it better to get students to do this type of generation activity, or should I just get them to classify lots of examples? So when they've learned what the definition of an increasing and decreasing sequence is, should I just give them a list of things and say which of these are increasing, which of these are decreasing, or should I ask them to produce some examples? Now, I'll not spoil the findings of that study. The main thing that I wanted to take away from that for today was just to point out one difference that I noticed in the results there, where the students who were generating lots of examples, I deliberately gave them a mix of formats to work with. So in the task sequence that they worked through, when they'd seen the definition of increasing and decreasing, here's an example of one of the questions. So the second question that they were asked was to give the formula for sequence that was decreasing, formula for one that was decreasing and bounded below, then one that was decreasing, bounded below, and U4 was equal to 1. So just successively adding more constraints, as we were seeing in the advice from Watson and Mason. And later on in the task sequence was where the JSXGraph examples that I was showing, where they appeared. So there, the students simply had to drag the points around to show an increasing sequence. And then they were asked to show a decreasing one, and then one that was neither increasing nor decreasing. And the thing that I thought was worth highlighting today, when we're talking about interactivity and visualization, was just the difference in success that we saw there. So this is a figure from the paper. Essentially what to look at is the G2 bars down here. The students were only getting this algebraic expression correct about half of the time, whereas when it was a more interactive visual representation, they were getting it correct much more often, and they were almost flawless there, in fact. Now, there's a whole lot else going on here that maybe they're just getting more familiar with this type of task, this concept, so you can see they're naturally getting better as they go through, and they're getting feedback on their earlier tasks. So there's maybe something confounding it there. But I think there is something to be said for sometimes the student will know what they're trying to say here, but find it hard to input in algebraic form. So having this ability to get them to show us, and you don't necessarily need to know what the formula is, as long as you can show me, that maybe captures something that we do sometimes want to be able to assess. Okay, and the second thing that I wanted to highlight, so I'm just wondering, am I okay for time? Yeah, good. Is it better to be using e-assessment or to be getting the students to do this on paper? So this is moving on to the functions example that I was showing. So this was the first question in the sequence, where they're just asked to graph an example where the image was 0, 1/2. And what I did, working together with Ben Davies and Paola Iannoni, was really wanting to explore the effect of doing this task online through Stack versus doing it on paper. So to really get at that, we were able to embed this task in the assessment for a first-year course on proofs and problem solving, where this was exactly relevant to a topic that the students were doing in week 8 of the course. So in 2019-20, this was when we put it into the Stack quiz. So each week the students had a reading quiz to do, and we stuck in the 4 Stack questions of the type that I was demonstrating a minute ago. Then the following year, we took it out of the Stack quiz and put it onto the written homework. And we got, again, 300 or so students with exactly the same prompts, but this time the responses were written. And then at that time, we'd moved to using Gradescope, so we've got them all scanned in, and we're able to look through them at our leisure. Not that it was so leisurely looking through 300 plus students' pieces of work, but it's a job that had to be done. So this was the task sequence, and this is how it appeared to the students when they were asked to do it in written form. So the first question having image 0, 1/2, and then the second part adding the constraint that the example is not injective. And then there were further parts, but I'm just going to focus on the first 2 for today. So this was the question that I was demonstrating a minute ago. As I was showing, the students can take the points A, B, C, and D and move them around, and they will see the piecewise linear function transforming before their eyes. Now, the first sort of striking thing that we saw from this data was that the students doing this on paper were much more successful at it than the students doing it on stack. So that was quite noticeable, certainly when obviously the chronology is different here. So we did the stack data collection first, and that sort of in a way motivated wanting to see, can the students actually do this on paper? And yes, it does seem that they were more successful at it when working on paper. So we delved a little deeper into the sorts of examples that the students were generating. So looking at the first task on paper, so we had 286 correct responses. The vast majority of them were doing this very simple example. Perhaps it was the first thing that came to your mind as well. But we did see, a few other types of things going on as well. On the stack version of things, that was also common. So we saw the essentially y equals x over 2 example. But actually the most common example was this one. And that is basically, I think, because the points that the students could drag around were constrained to be on the grid. And it wasn't straightforward for them to get them into a position that would create the straight line. So it was easier for them to make this slightly bumpy version of it, but perhaps they had the same idea. And again, we did see a range of other things going on as well. But where it got interesting was task B. So this is where we're asking for the added constraint that the function that they give is not injective. And here, the most common example that we saw in the written version of things was a quadratic. And as you may be thinking, that's obviously not going to be possible in the stack version of things. Other common examples that we saw in the written version of things, there was this sort of cusp type example, various wiggly things. So that's a sort of cubic example, and just lots of weird and wonderful other things that students were coming up with as well. And really what we're seeing in the stack version of the task is that students are being pushed into using this bottom left type of example, so piecewise linear functions, which are apparently not the range of things that they're most comfortable using. So the most common examples that we were seeing through stack, to my eye, were kind of looking a bit like they tried to make the parabola as best they could using the tool that they were given. And this example of the sort of V shape we were seeing, and various other shapes as well. But I thought that was quite striking to see the parabola being sort of ruled out, but the students were trying to do it anyway. So the main things that we're taking away from that bigger piece of research with the 300 and odd students in each group, the two key takeaways were that the students seemed to be doing better on the written version, and that we were seeing a greater diversity in the examples that they were able to give there. Perhaps not surprising based on the constraints that we'd imposed in the interface. So we followed up on this because we wanted to learn a bit more in detail about what was going on, with some interviews with students from the same course in the next year. So we had 11 students do it in person on paper and 8 students do it online using Stack. And that really let us see what was going on when they were interacting with these interactive visualizations. And I'll not dwell on this too much, but there were different strategies that we were looking at that have been identified in previous research, strategies that students can use to generate examples. So broadly speaking, trial and error is coming up with something, maybe just remembering something or plucking something out of thin air and checking if it works. Transformation is taking an example that doesn't quite work and modifying it so it does. So for one of the questions, I think it was the final part, we saw a student start with the graph at the top and then make this slight tweak to the position of point A so that it became a correct example. And then the most probably sophisticated strategy is to start with the definitions of things and figure out what they mean. So for the very first task, the fact that it's a function from 0, 1 to 0, 1, and its image is 0, 1/2, the student we saw in the interview conclude that it has to be in this box here, and now I just need to draw in anything. And so that's what they did. So we went through all the interviews that we carried out and going back over the recordings, looking for what strategies the students were using. And we found quite a lot of trial and error going on to begin with. So this is for students working on paper. There was a bunch of transformation happening in the third part, which really invited them to take the previous answer to part B and transform it. And quite a lot of them were using this more sophisticated strategy, writing down the definition and thinking about what it means. Whereas when we looked at the stack interviews, it was really the trial and error strategy there that was dominating, and there was really not so much of this definition analysis. So that was a really striking finding, that the students were, when they were using the e-assessment version of things, were more inclined to be adopting this less sophisticated strategy, and were less successful overall as well. So that's maybe a slight downer to end on. There is a potential note of caution there, I guess, that it's not necessarily a good thing to just make it an e-assessment and therefore it will all be fine. So, I think it does bring advantages to being able to do this at scale and give students quick feedback, but we need to be mindful of the challenges that are there. So using the interface, and the question earlier about accessibility is on my mind as well. Having seen the students kind of struggle to figure out how to move the points around, and there was one student that actually clicked on one of the joining lines between A and B, and it suddenly moved all the points around. It's not a familiar interface to the students, and that requires some learning in itself. There was an extra challenge in the interface that we chose, that perhaps the answers that were coming to their mind were not ones that they could readily express in the tool that we'd given them. And for some reason that I don't understand, they were using different strategies than the students who were working on paper. And it may just be that they're used to sitting down and interacting with quizzes in a sort of not very deep way. I don't know. But another possible side benefit to this is that this added challenge could be beneficial, actually pushing the students to look at these types of examples that they wouldn't otherwise consider. They could benefit from engaging with tasks like this. Okay, so that's me. And as promised, there's the link there to get onto the webpage that I was showing you with the examples, and I'll be updating that soon so that you're able to download the stack code and do with that what you will. Okay, thanks very much.
Thank you, George. We've got time for one question or two. Were you surprised by that finding? Because it surprised me that people did better, a lot better in actual and in assignments.
Yeah, and I think I've maybe glossed over some of the details there, that the fact that they were doing the quiz slightly earlier in the week that year versus the written homework was at the end of the week, so it might just be that they've got more deeply into the topic by that point. So there's that slight caveat with the big results from the first part of the study. But actually we saw the same thing happen in the interviews, and the students who were doing the stack version of things were overall less successful, and it really did mirror the results from the first round. So I think there is something in the advice that I always give the students in my online course, is that they shouldn't be just sitting down at the quiz and expecting to type in the answer. they should be doing working out on paper, and it's not going to be something that they can just do in their head and type in the answer to. So I think there is just maybe something about the way students interact with the assessment where they maybe expect to be able to do it without the working out.
Yeah.